Hi, in this video we will learn about the properties of inverse matrices. And we will see how the inverse of matrix work with the other operations that we have learned so far for matrices. Okay, so the first thing is that the inverse of an invertible matrix is unique. Meaning that, well, if I find an inverse for a matrix, so let's say I found AB equals to identity, well, both from left and right, and you find another one, so let me write B1, and then you find another matrix B2 equals to I and B2A. These B1, B2 need to be the same. It is unique. We cannot find more than one inverse. Okay, so why is that? So you see, just let me just show you. This is B1 is inverse, yes. Then you can multiply both sides by B2 from the left. So it means that B2 of A, B1 is going to be equal to B2 times identity. Well, I can use the associativity and write B2 times A times B1, and B2 times identity is just B2 itself. Now you see that B2 times A is identity. That means that we have identity times B1 is equal to B2. As a result, we have B1 is equal to B2. That means that no matter who finds an inverse, a matrix, when you multiply to A, you get identity matrix. Those matrices are going to be same. Okay. The second property is that inverse of a matrix is invertible. So A inverse, and its inverse is A itself. Well, this is very interesting, that basically inverse of A inverse is a matrix that when you multiply to it from left and from the right, you get identity matrix. But we know that A inverse itself, when you multiply to A from left or from right, this is going to be identity matrix. Uniqueness of inverse matrix says that, okay, this guy that when you multiply to A inverse from left and right, and you got identity, it needs to be equal to A. So that is what we have. Inverse of inverse is the original matrix. Then the third property, how about when you multiply matrix, invertible matrix by a constant, a scalar multiplication and inverse? Well, we assume that C is non-zero. If C is non-zero, then we are trying, basically, we know that A inverse times A and A inverse is equal to identity. Now, if you multiply A by C, A inverse, we know that we can bring up C and write A inverse A, and this is C times identity. I'm interested in finding I, so I divide both sides by inverse. So C, 1 over C A inverse times CA is equal to identity. This means what? This means that we found a matrix. When you multiply from left to CA, you get identity. You can do a similar trick, and you will see that the inverse of CA here is 1 over CA inverse. Basically, the inverse of the scalar times the inverse of the matrix. That was the third property. The fourth property is, how about matrix multiplication and A inverse? Here I'm assuming A and B are two invertible matrices which can be multiplied. So if A is invertible and B is invertible, what is the inverse of AB? See, okay, so I have A times A inverse equal to identity. And also I have B times B inverse from both left and right. These are identity, yes? Now I have AB. I'm looking for a matrix. When I multiply this whole thing from left or from right, I get identity matrix. Okay? So I can go one by one and try to first cancel B. So I can write AB times B inverse. So this way I cancel B and then I cancel A inverse. This will give me identity matrix. This whole thing, if I multiply it to AB from the right, from the left also, so B inverse, A inverse, AB would do the same job. So by the associativity, you can consider this piece first, and then you will have B inverse times B, which will give us the identity. So this means what? This means that the matrix, when you multiply AB2, gives us identity. This is the same as B inverse A inverse. It is very important I change the order. In general, this guy has general form. Let's say we have A1, A2, AN, and all of them are invertible. Then if you want to find the inverse of the product of these guys, you have to first find inverse of the last matrix, and then the one before that, multiply up to a one inverse to the end. So you just can prove this thing just using the trick that we used above. So with product, it works nicely, but you have to be careful. You have to change the order of the product as you see that. Okay, very nice. And what about the transpose and inverse? So if I have an invertible matrix, what is the inverse of its transpose? You see, I have inverse, so that means that we have this both from right and both from left. Okay, then take the transpose of both sides, or all three sides. A inverse transpose, A I transpose, A inverse, A transpose. Yes. So transpose, remember that when you apply transpose over product, you will get the inverse here. So the order changes. Transpose of identity as identity, so this is A transpose A inverse transpose. You see what happened here is that I found the matrix. When I multiply with A transpose from the left or from the right, I get identity. This means that the inverse of A transpose is A, you first find transpose and then find the inverse. And the last thing, which will give us very nice property, I'll show you something here. So what about if I have A, which is invertible, to the power n inverse? So A to the power n, what should I multiply to this guy to get identity? So this is same thing as A times up to A. And we learned that if you have inverse of these guys, so you have to write the inverse of each one, multiply, but in opposite order. So this guy inverse up to this guy inverse at the end. And this is same thing as A inverse to the power n. So this is A inverse to the power n. And power and transpose, you can see what happens. This gives us a good idea that, well, so far the powers that we were defining was for positive integers or 0. How about the negative one? So this is the negative definition. If A is invertible, when we say A to the power negative n for an integer number, positive integer, then what do we mean by this? This is the definition. It means that you multiply A inverse n times to itself, or in other words, this is A inverse to the power n, or you can say, well, okay, this is A n to the power negative 1, which is the same thing. Well, these properties you have to know, you have to be able to use. Let me just finish the video by one example that, okay, so use now these properties to solve a matrix equation given here. So we are looking for an X, B, and A are square invertible matrices. And we have these properties. I want to solve this guy. In other words, we want to isolate X. Keep X one side, the rest the other side. First thing is that, okay, to get rid of this A, we have to somehow cancel that A from there, yes? But to cancel A, I need to multiply A. Here, only I can multiply from the right. So this will be what will happen. So XB transpose A, oh, by inverse of A, sorry. Okay, this is something here, A inverse. What is this guy? This is AB inverse, AB inverse. Yeah. Okay, now this gives me, well, use associativity. This will give identity for us. And the transpose here will give a B transpose X transpose times identity equals to A, B inverse, A, B inverse, A inverse. We cannot do anything more than that. You cannot bring this here and cancel A. We don't know if A and B commute or not. So you have to be very careful. Now identity goes away itself. And this is A, B inverse, A, B inverse, A inverse. And then now I can, B is invertible. I can use the property that B transpose has inverse. And if I multiply it from the left by the B transpose T, then we will have this guy, A, B inverse, A, B inverse, A inverse. And well, these two guys cancel each other, and I can write X transpose is equal to B. B transpose, oh, I forgot to multiply this guy by the transpose from the left. Sorry. This is B transpose inverse. B transpose inverse is the same thing as B inverse transpose. We are using that property. And I don't need to put any brackets because of the associativity. What did happen here? Okay, I know what happened. This is the one. And well, to find X itself, we have to find the transpose of both sides, and that will give us everything we want to find. Transpose. Here, a transpose of transpose is transpose. X is isolated, and the right-hand side is our solution, our answer here. So transpose, you have the same things, but the order changes. I know it is a little bit huge, but you have to be careful. So here, the last one is B inverse transpose, which the transpose of transpose cancel each other, and then you get. I know you may want to commute these guys and write one expression, but you cannot commute because you don't know if A and B are commuting matrices. AB needs not to be equal to BA. Okay, so these were the properties of inverse matrices, and you have to be able to use them as we saw in this example.